intensity level scale. Threshold of hearing is the lowest.
It's confusing in itself, just being the same number.
And what are we getting for part B here? 68 and a half decibels. Yeah. Make sure you write the units for these, and make sure you plug it in right. If you're not getting either one of these numbers on your calculator, call me over and we'll fix it now. You have to be able to plug these in or know how to plug them in correctly.
So, you said we just have to memorize the one that's boxed? the one
Yeah, that's the equation for intensity level. This constant here I'll give you, and it'll be written down as I not, so you'll know right where it goes in the equation, hopefully. You all getting this who are trying? Okay. If you're not getting it and you are too embarrassed to say something, that's fine, ask me after class, but we're all family here, right? No need to be embarrassed. We are all wrong, almost all the time, right?
Unless you're married, then you're wrong all the time.
Well played.
See my hand. I love being right.
Smart man.
Okay, so let's talk about the Doppler effect. Now I've got a few things I think that are still in here that I'll just put up here on the Doppler effect. When you hear a different sound frequency because of a moving source, or if you're moving, when you hear that, like when you're out on the road and you hear a siren driving by, you probably hear it a little bit differently when it's coming toward or away. That's not because it's just getting closer so it's getting louder. Yes, you do hear it louder as it's closer, but you also hear a different frequency when it's coming toward or away from you. Have you all noticed that?
Yeah.
You might have noticed it. If any of you watch NASCAR, James, you might watch NASCAR.
No, actually, I don't watch it anymore.
I know that was wrong, I'm just joking.
I used to.
But you probably heard it there too when the cars go on the track, and if you're sitting one place or you're on TV, you can hear that effect when they're going around and passing by wherever the microphone is. All these things you could take if you went at home or you took your Beats by Dr. Dre, turn them up real loud, whirl them around your head, you probably hear that frequency change too, anything like that you can produce a sound with. If you hear a different frequency because of motion, whether it's you or whether it's the source, then that effect is called the Doppler effect. When the frequencies or when the observer is moving towards you or the source is moving towards you, you hear a certain frequency that's higher. If it's moving away, it's lower. Okay? You should know those two things. When it's higher coming towards you, lower going away. But if you don't have those memorized, it usually won't kill you. It's good to know those so that when you get an answer, you know if it's right or wrong, at least with what it should be. Right? You should be able to expect your frequency to go high or low as long as you know what's moving and how things are moving. But that's not something that I usually ask as just a question on the exam to tell me if it's higher or lower. I'm just going to give you a Doppler problem where you're going to solve for the speed of the source or the observer or one of these frequencies. But it's very useful to know how it works and what that is when it's higher or lower. Okay. The equation on the next page here, did you all get a chance to write that down?
If it's approaching and the frequency is higher, then that means the waves are shorter.
If the frequency is higher, then the wavelength goes bigger or smaller?
And they're all-
Shorter wavelength with the higher
the other
frequency.
way.
Yeah. This equation looks ugly, probably to some of you. There's plus and minus signs here on top and a minus and plus there on the bottom. I'm going to give you that equation on the exam on Tuesday. You just need to know how to use it. Okay. What we have here with these signs, and I'll tell you what all these O's and B's and everything mean in here in just a second. But the signs that are in here just tell you whether you're moving toward or away. Okay. You use the upper signs if the objects are moving toward each other, and they could both be moving or one could be at rest. But if they're moving toward each other, you use the top signs, the upper signs here. The plus there, the minus there. If they're moving away, then you would use minus on top and the plus on the bottom. So you do need to know when to use the upper or the the lower signs, but that equation I'm gonna give you on the exam. Okay, let me write down what everything means in there now. The FO is the observed frequency. FS is the source. We have VO, which is the speed of the observer, the person or the thing that is detecting the sound. VS is the speed of the source. V is the speed of sound. Okay. So sound and speed and source, I'll start with an S. Don't get your S right here mixed up. S is for source, O is for observer, nothing is for the speed of sound. Okay. Just don't, make sure you don't mix up your source and your sound down here with the S's. Okay. They are written as V's for velocity, or the variable that we use for velocity, but these are all speeds, these are all magnitudes of the velocity. So don't think that because it's a V that it's a vector quantity where you need to worry about the direction having a plus or a minus sign that would go with those V's. These are always just positive numbers. The directions are already taken into account by using the sign conventions that we have here with the plus and minus, or the minus and plus signs there on those two terms there. Okay. We'll go through a couple of examples here where I kind of show you how to use the plus and minus signs here, but just you have to make sure you remember that part, that we're using upper signs if they're moving toward, and the lower signs if they're moving away. And the upper signs just mean the signs here on the top, plus and the minus there. The lower signs would be minus there and plus there. Okay? It's pretty easy, I think, to distinguish between a Doppler effect problem and a standing wave problem. They're completely different. There's a source of sound, there's a frequency that you're detecting. I'm not saying it's going to be easy, but on this exam, you can usually tell right away what kind of problem it is. If it's a Doppler effect, if it's a standing wave, you'll know, and that's a good thing. Because before, you may have had no idea if you were supposed to be using forces or kinematics or energy or anything like that. That's another reason why this test could be easier. There are going to be problems in all those different standing waves. There will be a Doppler problem. This is usually a 15-point problem or so for the Doppler effect. And then you have about 30 to 35 points worth of points on the standing waves. I already think I told you that the first day of the lecture, I think I counted up about 38 points for all those things from the first day of the unit. That may not add up to 100 yet, but we're getting close.
So will you give us all of those, or do we need to solve for a variable?
We're going to solve for something here. This won't be as easy as plugging in and solving for the F right here. And the first one that we do, I think I'll do one where we just solve for that observed frequency, just to kind of show you how to choose the upper and lower signs. But then they would be harder with the math, a little bit longer if you have to solve for something in here. So we'll do that too, to kind of just practice reminding ourselves how to get rid of that fraction. But you could solve for anything in there. You would probably think they're easiest when you're solving for FO, because it's already solved for you. I can tell you though that on the exam, that may be part of a problem, but at some point you're also going to have to solve for something in here. Okay? The whole thing won't just be plugging directly into the equation and solving. Okay? So let's go to the third problem on here, where you have two submarines that are underwater and approaching each other head on. Okay? So I'm just going to draw two submarines like this. I'll call this one over here on the left A, and the one over here on the right B. Submarine A has a speed of 12 meters per second, and submarine B is 8. So they're moving toward each other here. They're approaching head on. So I know that this one's going this way to the right. Let me take this arrow off here. I'm just going to put the arrow on top here. And I'm going to call this V. I don't want to call it VA. I want to call it whichever V it should be for the equations. Which one do you think that's going to be?
A is the source.
A is the source, sending off some sound, and then B is going to detect that sound. So let this be the source. I'll call this VS. You may want to just kind of slow down at the beginning and just make sure you write down this is the source, this is the observer. Sometimes you'll see little wave fronts like this showing which one's producing the sound. Might be drawn like that. We sometimes also just draw it where we actually show the wave and then put the frequency on the wave like that. Those would be two ways that you might see the sound drawn on a picture. Something like this, these are what we call the wave fronts. This is just kind of a drawing of what the wave or the frequency might look like. But there's no scale to either one of these. And that's how you might see it though in some of your pictures. Just really slow down at the beginning, make sure you know which one is which. You can probably do it without a picture sometimes if you really know where everything goes in the equation, but just slow down and get a picture drawn, make sure you're clear on the source, the observer. Let's label everything here. We know B is moving this way, so we're going to call this, what V would that be? That's your VO. We have, I think we gave you the speed of sound and water here. And we gave you the frequencies here. So let's also write down sub A, which is sending out that 1550 hertz wave here. This is the source, so we'll call that FS. We're having FO, which is observed over here. That's unknown. So I'll just put a question mark there. And the speed is 1522 for the speed of that sound wave here. So we'll just call that V for the speed of the wave. As long as you have all these straight, then it's just a matter of using your equation. So you've got FO is equal to V. So then here's where you choose the signs. If they're moving toward each other, then you choose the upper sign. So on top there in the numerator, you've got V plus VO. Then you have V minus VS down there on the bottom. So see what I mean with the upper signs? Just the plus and minus there. You'll have that equation written for you. Just choose those signs correctly, and now you have the equation you can work with. But you'll have to choose those signs first before you start plugging anything in.
So wouldn't be a plus sign on the bottom too?
No, because you're using the upper signs,
Use the upper
the top sign here and the top sign there.
When they're moving away from each other, you
That
do
minus and the plus. Yeah. Now, your book is going to show you 3 or 4 different equations for the Doppler effect. This is the one that summarizes them all into one equation. Your book will probably give you an equation for the case where you have a stationary observer, a stationary source, if they're moving toward or away, and they'll write it out separately as different equations. Don't worry about looking at all those. Use that equation there and just know how to choose those signs. That'll work for all cases. You might be able to find an equation in your book that would work just for this situation, which would look just like that, but this will work all the time as long as you know your signs and how to choose them in that equation. So just work with that when you're doing the practice problems and the homework, because that's what I'm giving you next week. Okay. So we know the VO and the VS, which I haven't written down yet, but what is the VS? 12, I think the other one was 8, right? Okay, so I'll just write them down here so we have it all listed out here with the picture, but we can just plug all those in here. The observed frequency detected by B here is what we're looking for. So you've got your 1522 plus the VO, which is 8. The source frequency is at 1550 hertz. And then you're dividing by the 1522 for the speed of sound there, minus the 12, which was the source frequency of submarine A. parentheses around that whole thing. Like it was there to begin with. But there, you just plug it in. What kind of number should we expect here? Compared to the source. Higher if they're moving toward, lower when it's moving away. And again, you can figure it out if you trust your math and your answer's right here, so you don't have to have that memorized, but it's very useful because it's common for people just to mix up numbers sometimes, and it's just, you can do these, just keep it all straight. And for me, I definitely want to write it out like this with the O's and the S's here. I don't want to be reading through that problem statement again, trying to figure out where the 8 and where the 12 goes. Like always, I mean, it's so clean for me to put right here. I don't want to have to go back and reread. If you do this, though, we should expect a number that's higher. You'll get that here when you plug those numbers in. A frequency of 1570.5 hertz for the observed frequency there. So, just add a part on here. If A and B are moving away from each other at the same speeds that we had there. Then, let's solve for the same thing. And let's just show how to work with that equation.
You just change the sign.
Yeah, I'm just writing it down so you have it, and so you'll just see and remind yourself of what the rules here are. You've got your V now, you want to use the lower sign, so now you go to the minus sign up there on top, and you have V, and then plus a VS times that S there. It's the exact same thing, you just switch the signs. And this observed frequency should be higher or lower than the 1550. Lower, moving away, here you'll get a 1530 hertz frequency there. That's the only difference on the equation. Only those two options. Okay, so let's go ahead and, I'm going to draw a new picture for part B. Some of these things are going to switch now. They are still moving toward each other, like they are here. But now, we want the sound frequency that A is going to detect after the wave reflects off of B and then bounces back. So part of the wave is reflected back to A. What frequency does A detect for that reflected wave? Okay, so this is now the source. This is the observer. Just switch these now. This is the source. This is the observer. We still have the same speeds here, so my VO is, how much was that one? That was the 12, right, for A? And then the source is B now, which is the 8. Okay. The observed frequency over here for A is unknown now, but the source frequency for B is what?
The answer, or what we just got.
The answer for part A here, the 1570.5 hertz there. So if you want to draw it on here, now it's this wave being reflected, sent back this way. And you're doing the exact same thing again with the equation. Set up the Doppler equation one more time. So you got your V, we're using the same one here because they're still moving toward each other, so you have your upper signs there again, the V plus VO, and the V minus VS times the source frequency. And it's just new numbers in here now, because we switched the source and the observer. So you have your 15, was it 22 for the speed?
Yeah.
Okay. 1522 plus the 12 over the 1522 again. Now minus the source, which is the 8. And then multiplied by the 1570, which was the source frequency now. And this number should be bigger than the 1570, because they're moving toward each other, so we'll get another higher frequency here of 1591 hertz here for that wave. Everybody good with that?